All right, people. Toolkit number 14. We're going to describe functions. So here's a function. We're going to call this f of x. We're going to give it some arrows at the end because they weren't there before. We're going to make this official. All right. So just checking out this function, get a little feel for it before we describe it. All right. Imagine you were on a roller coaster ride, and this was a roller coaster, right? What would it feel like? Going down, up, right? Then heading off. Right? So kind of get a feel for it first, and then let's talk about some things. Okay? So when we talk about domain, when we're talking about domain, it means what x values work. Okay? I'm going to put that in parentheses. What x values are in play? Let's start at the origin and go to the left. Do you think this eventually goes to forever to the left? I think so. Looking at this arrow, it doesn't look like it's going to come back on itself. It's going to go up really high, right? But it's going to keep going. If I go to a million over here and go up, there's going to be a point where this finally crosses. It's going to be really high. It's going to be way, way up there, but it's eventually going to get there, right? What about to the right side? So if we start at the origin and go this way, right? The x values are at 1, 2, 3, 4, 5, 6, 7, 8, 9. Are they eventually going to get to 10? Are they eventually going to get to 100 and a million? Yeah, they're eventually going to get there. It's going to take a long time to get there because it's getting so high up there, right? But it's eventually going to get there. Okay. So when this is the case, it goes from negative infinity all the way to positive infinity. We can say this a couple different ways. We can say all real numbers are the domain, right? We can say fancy R like that, right? It's an R kind of cursive with two lines. And I love doing that. That used to be my signature. It would be like Rick Reboff, and there would be two R's that look just like that. I really like the all reals number. All right. And the third way to do it is with interval notation. You may have seen this in Algebra 2. We're going to bring it out because in pre-calculus, it's a big deal. Okay. So what we say is at the left endpoint, what is the farthest it can go to the left? Well, it can go to negative infinity to the left. So I'm going to write negative infinity. Then I'm going to do a comma. And it's going to be how far can we go to the right? Where does it end on the right? And that's going to be positive infinity. So the domain is everywhere from negative infinity to positive infinity. Okay. And then what we're going to do is we are going to decide, does it ever get there? So does this endpoint count? If the endpoint doesn't count, we put a parenthesis. You can't get to negative infinity. So we're going to put kind of a soft ending here. We'll see a solid endpoint later. So this means parentheses mean that it does not get there, does not count, doesn't get there. Okay. You will see later on when we have brackets, brackets means it does count. Okay. That the endpoint is part of the range. We can't get to negative infinity. We can't get to positive infinity. So we put these little soft endpoints. Okay. Range. Well, if domain was what x values work, range is going to be what y values work. Okay. So what y values work. So I look at this and I go, well, the y values go up forever right here. So that's going to go to positive infinity. Okay. So when I write it in interval notation, oops, I don't know that that's going to be the case. When I write it in interval notation, I know it's going to go to positive infinity and it can't get there, right? Well, how low can it go? So what's the lowest point it gets to? Oh, snap. It gets to, let's say that it does get to this point. Let's count. One, two, three, four, seven, eight. Looks like it's -8. Okay, I could be wrong. I think it's -8. It gets down to -8. So its lowest point is -8. And does it get there? I'm going to assume it does. Okay. If I gave you this on an exam and you said it didn't count, I'd be like, okay, maybe it didn't. I don't know. If I put a point there and I said this is 1, 2, 3, 4, 4.2 comma 8, and I'm showing you that this point does exist, that it does get to, um, oops, sorry, negative 8. It does get to a value of negative 8 when the x value is 4.2, then you would definitely want to put this in. Okay? So this means the endpoint does count. It does reach negative 8. That's part of the range, but it goes to positive infinity. We can't get there. Okie dokie. You could also write it this way. Y is greater than or equal to 8. Up here for all real, well, you can't really do that with that, right? X is all real numbers. All right. Increasing, decreasing. There's also constant, right? Constant means you're holding your position as you go out. This one does not have any constant. It's either increasing or decreasing. The way that you do this is for both increasing and decreasing, you get on the roller coaster on the far left side. Okay. And then you go for a ride. I wrote that there. Sorry. Get on roller coaster on far left side. So that's how you figure out if you're increasing or decreasing. You ready? That's just step one. Don't worry. You're like, what do you mean get on a roller coaster? It's stupid, mystery buff. Here's the farthest left that this graph goes. Get on the roller coaster and ride that roller coaster. What's happening? Are you decreasing or increasing people as you move to the right? Yeah, this is decreasing, right? So this is decreasing, right? What happens when you hit this low point and you start going this way? Yeah, it's increasing, right? And then what happens? You're decreasing again, right? So this part here, you're decreasing. What about from here to here? Yeah, you're increasing. And then from here to here, you're decreasing. And then from here to infinity, you are increasing, right? There we go. So this is saying where are the increasing points? So from left to right, it is going up. For decreasing, as we go from left to right, it's going down. Constant would be as we go from left to right if it had like a straight across line, right? So the increasing ones are from here to here. That looks like about negative 1, 2, 3.5 to negative 1.5. So I'm going to go negative 3.5 to negative 1.5. I'm going to unite that. Oops, sorry. I'll make sure I show you that. So from negative 3.5 to negative 1.5, it's decreasing. And then I'm going to use this. It means unite, right? We're also saying or, right? The next one is from, I'm going to call it 0 to 2.2. So 0 comma 2.2. Doing the best I can here, and that's fine if you do the same thing. Then we decrease, and now it goes up, and that looks like from about 4.2 and beyond. So 4.2 to positive infinity. It's going to increase from that point on. Okay. I'm putting not including here, and that's pretty typical, right? So these endpoints don't count because at that endpoint, that's where it's changing, right? So I go with that. Where is it decreasing? Let's go. Negative infinity all the way to, what did I call that? Negative 3.5. And then that's going to unionize with, looks like 1.5 to 0, negative 1.5 to 0. And that's going to union with this one, which was what, 2.2 down to 4.2. Notice it's kind of the same numbers, right? Because it's in between those. And that's it. There we go. Increasing, decreasing. Not hard to do, right? You just have to remember where to get on the roller coaster. Get on it from here. And then I just like to mark up my graph like this. And that makes it a heck of a lot easier to do. All right. Do we have any x-intercepts? Okay. So where does it cross? Where cross x-axis? Wow, that is fantastic English. Where cross x-axis? Take a guess what y-axis is. Where, if you want to fix that because you actually care about proper use of grammar, and you should, Where across y-axis. All right. Summertime. Look, summertime back there. Grammar's hard when it's going off out there. All right, where's it crossing the x-axis? It looks like negative one, two, three, four. Um, Pretty close to negative two. So I'm just going to say the points. It crosses the x-axis at negative four, negative 2.1. This looks like negative zero point 0.7 or something like that. I'm guessing. I'm giving it my best go. Okay, and that's fine. That's all I would ask of you in a problem like this. Unless I gave you the actual points where it crossed, then you would want to be a little bit more accurate than this. Looks like zero point 0.9, 0.9, then again at 1, 2, 3, and then again at 4, 5. Positive. There we go. There's where it crosses the x-axis. And with a function, it can cross that x-axis a whole bunch of times. It can only cross the y-axis once if it's an actual function. And where is that at? That looks like about negative zero point 0.8. Okay, cool. There we go. We got our x-intercepts, we got our y-intercepts. All right. Whew. A lot to do, right? Maxima. Okay. Maxima is a high point. Um, Local means it's higher than any point to the left or right. Higher than left or right. So immediately to the left or immediately to the right, it's the highest point right there, right? Global, and we're going to talk more about this later once we get to more calculusy stuff. This is a really important concept in calculus, finding that high point or the low point. Um, Global means it's higher than any other point in the function. Okay, it's the highest. So for instance, Windy Hill is a local high point, right? It's not the highest point on Earth. It's not even the highest point in California, but Windy Hill is a local high point, right? So that would be a local maxima. Okay, whereas what is it called? Um, why am I blanking? Um, Everest, there we go. Mount Everest is a global high point. It is the highest point on Earth. You can't get higher than that. So that would be a global maxima. There's lots and lots of local maxima. There is only one global maxima. Unless there was another mountain that was exactly the same height, then they would tie. They'd be both global maxima. All right. Minimum, take a wild guess. Low point, right? Same idea as up above, right? If it's local, it means it's the lowest point to the left or right. There's not a lower point than this, right? Portola Valley at some point is a local minima. But I think, at least in California, if we made California the globe, um, Death Valley would be the lowest point. It might be the lowest point on Earth, I think. I'm not sure. I'm not 100% sure. You can tell me in class if you know that I'm wrong, because it's fun to tell Mr. Bob he's wrong. And I'm okay with it. I like to learn. All right. So same idea as before. All right. So let's find some local maximas. And is there a global maxima? Sometimes it's fun to start with the global, right? So is there a global high point? No, there's not. Okay. Because this goes forever, right? It keeps getting higher and higher and higher and higher and higher. It'd be like if Mount Everest just kept growing. And it actually is growing, right? By like a tenth of an inch a year. Okay. So I guess maybe it's, I don't know. But if it was growing by 5,000 feet per year, it'd be like, oh, well, let's kind of keep going. I guess it is kind of the highest, but whatever. So for this one, we say none, unless it's like set in stone. This is the highest. We'll say there is no global high point. There's no maxima because it goes forever. We can't find it. It keeps going. Okay. But the local ones, there's a lot. Usually we define them as where the X value is at that point, right? So at negative 1 point, what was that? Negative 1.5, right? So at X equals negative 1.5, there's a max, right? We see it right there. Where else is there a local maximum, local high point? Right here, right? I think we call that 2.2 and 2.2. So I'm saying where the x value is. I could also say the point, 1.5 comma zero point 0.8, 2.1 comma 2.7. You can name the point or you can name the x value. Okay, that's the common way to do it. All right, what about low points? Minimum. Let's start with local. Let's start with global. Is there a low point, a point that is lower than any other point on the whole thing? Yeah, there it is right there. So we could say it's this point, or we could call the x value. So global at x equals, I think we called it 4.2, but it's okay to do the point as well. You could say global at 4.2 comma negative 8. Okay. What about local low points? Are there any other local ones? Yeah, there's one here, right? And one here, right? At this point, to the left and to the right are higher than this. So these are local. And that is at negative 1, 2, 3.5 and at 0, right? X equals negative 3.5 and 0. So those are the two local mins. You could probably call the global a local one as well, but it's so special, we'll just call it the global. All right, last thing to do here. We're going to talk about left end behavior and right end behavior. What happens to our y values as x goes towards infinity, positive infinity, and as x goes towards negative infinity? So what happens when we go way to the left? What happens to the y values? What happens is we go to the right, right? As the x values get bigger and bigger, right? So the way we do this is we actually say it in words. As x approaches negative infinity, as we go really far to the left, the y values get closer to what? And we can also do as x goes towards positive infinity, as we go out to the right, my y values get closer to what? So let's check it out. As we go to the left, let's do the first one. So here we are traveling as we go to the left. Oh, my pen froze there. It's so weird. Come on, bruh. You got this. Let's switch camera and come back. Hold on. Scary, big Mr. Rebuff. Somehow, for some reason, it wanted to talk to my phone. Okay. You don't want to see this. Why? Give it 2 seconds here. Hold on. Pause. Pause. Oh my gosh, that was crazy. You had to see my face really big. I apologize. Probably ruined your night. Hopefully you ate before that because now your appetite's gone. Sorry. All right, where were we? As x goes towards negative infinity. So what happens to our y values as we go far to the left? So let's go on a trip. So here we are. Let's go. Let's keep going left, keep going left, keep going left, keep going left. Where are our y values going? Oh my God. Oh my God. They're heading off to positive infinity, right? They're heading off to positive infinity. So we're going to say that as x goes towards negative infinity, our y values are heading off towards positive infinity. All right, let's do this one. As x goes towards positive infinity, as we go far and far to the right, what happens to our y values? All right, so let's go on a trip. Dad's driving, going to the right, going to the right. Oh my gosh, we're going down, 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 down. Oh my gosh, what's happening now? Whoa, oh, what's happening? Ooh, we are heading off to where? Positive infinity is. Okay. So, oh wow, I got both the left and right in the same thing. Mr. Reeboff. Oh my gosh. This is the left end behavior. This is the right end behavior. My bad. I put them all on the same one. I just did in behavior together. Sorry. So this is what happens as x goes towards positive infinity. I'm going to fix this. This is only x going towards negative infinity, and we'll just bring that one down. If you want to erase and rewrite, I'm sorry. I got so excited. I just did it early. All right, people, we'll see you.